And then I will So today we have Tariq Yasin from the University of Oxford, who's finishing his PhD with Harry Desmond, if I'm not mistaken, I hope I'm not, talking about inferring dark matter halo properties for H1 selected galaxies. Thank you very much for accepting our invitation. And yes,
cheers. So I'm speaking on a paper I wrote on the inferring dark matter halo properties for H1 selected galaxies. So in lambda CDM, dark matter halos are the virialized structures that form as the endpoint of the growth of perturbations under gravity. And in particular, at the center of these dark matter halos, baryons cool and form galaxies. So mapping out the set of correlations between the galaxies and the dark matter halos is called the galaxy halo connection, and finding this set of correlations is a sort of core endeavor of modern astrophysics. It's important for two reasons. First, to construct a consistent theory of galaxy formation within lambda CDM, and secondly, for the purpose of mapping out the dark matter distribution, which enables tests of the model itself. So we have techniques such as weak lensing that produce beautiful maps of the dark matter on larger scales. But in particular, what we're doing here is we're trying to infer where the dark matter is located on smaller scales around galaxies. So in this spirit, the aim is to get the tightest possible constraints on dark matter halo mass and concentration for the 23,000 galaxies visible in both the optical and the SDSS. And in the radio in alpha. To do this, we're going to do the following. We're going to get constraints on halo mass and concentration for each single galaxy using two different methods. The first of these is abundance matching, and the second is kinematics. And then we're going to combine them together to get tighter constraints. I'm going to talk about both of these methods in more detail. But essentially, abundance matching gives us a prediction for the property of the dark matter halos from cosmology. And kinematics is the more traditional method where, like Vera Rubin was doing, where you're looking at the motion of the gas or the stars in the galaxy, and you're inferring a missing mass from them. Right. So first, why the SDSS and why alpha? So alpha is a blind volume limited H1 survey. So it doesn't have very low resolution. Sorry, it doesn't have very high resolution. So for each galaxy, it detects the integrated H1 spectrum, which looks like this. So this is the H1 spectrum of the galaxy. If you put your aperture over the whole of it, you don't have any spatial resolution within the galaxy. And from that, you can get the H1 mass, and you also get this thing here, which is called the line width. And this width gives some measure of the kinematics of the galaxy, because it in some sense traces the motion of the gas disk. And from the SDSS, we get the stellar mass, and we get other galaxy properties such as the inclination. And so these are used in both abundance matching and our dynamical model. So the reason we get the kinematics from the H1 rather than the optical is, if you look at this to scale image over here, in the center there we have the optical disk of the galaxy. In red we have the H1 disk, which extends much further, and all the way over here this is the size of the dark matter halo. So to really probe the halo in any meaningful way, you need the H1 kinematics.
Sorry, Tariq, maybe you said it and I just missed it. How do you get the H1 mass from the line width?
So the H1 mass is you just integrate the total flux, and then you have a model for the sensitivity of your radio telescope, and that gives it to you. Okay. So in the same way as adding up all the luminosity of the galaxy. So a little intro to dark matter halo profiles. So in the 90s, Navarro, Frank, and White ran dark matter only simulations of galaxies, and they found the NFW profile, a universal halo profile, and that's at the top here. This is known as cusp, which means that a small radius, it goes as 1/r. And when we look when we look at structures in the universe, we find that there's some evidence that they do have this NFW profile matching the dark matter only simulations. There's some evidence for it from weak lensing or in higher mass galaxies. However, some structures we look at, especially smaller ones like dwarf galaxies, and we see they don't have a cusp profile. Instead, they have a chord profile, which is that where it levels off to a flat level at low radius. There's a lot of debate in literature. There's a lot of contradictory evidence. Some galaxies, you see people measure cusps. Some of the same ones, they measure cores. And this really applies across high mass and low mass galaxies. Some people argue it's just all systematics, and there's still a good chance that that there are just NFW profiles all around. We're going to stay agnostic on this and just fit the cusps and the chord profile as representative examples. Yeah.
How good an approximation would be spherical?
How good an approximation is spherical? So weak lensing experiments are beginning to probe the ellipticity of dark matter halos, and I think they're getting an ellipticity of about 0.8. So it's a decent approximation, but not perfect. But for the sorts of constraints we're going to get on the dark matter halo from kinematics, good enough. But maybe if you're considering the dynamics of, say, the Milky Way, where obviously the data is much better, then I think you need to take that into account. And this is a technical note, but we define a new concentration definition. So concentration measures how centrally concentrated the halo is. So the correlation of the matter in the halo with itself. So if you have high concentration, then most of the mass of the halo is towards the center. If you have low concentration, it's more spread out. Traditionally, concentration is just defined like this: the virial radius over the scale length. However, the scale length is sort of defined for a particular halo. So we just came up with this new definition where it's the virial radius over the radius containing 10% of the virial mass, just so we're parameterizing our models in the same way. But essentially, here I'm plotting the old definition against the new definition, and it's fairly similar. So anytime you see C 0.1, you can more or less read it off as the concentration you're used to.
Sorry, can you just say again why it is you chose to define a new one?
Yeah, so these profiles have a scale length in them, and traditionally people define concentration as the virial radius over the scale length. But the scale length is a different physical parameter for the different halo profiles. So we're just creating a universal parameter for both of them, but it's fairly similar to the old parameter. So you can, anywhere you see C 0.1, you can just read it off as concentration as you normally would.
Thanks.
So comparing kinematics and abundance matching is an interesting problem, and there's lots of previous literature on it. So here's an example from Post et al. 2019. So on the x-axis here, we've got halo mass, and on the y-axis, we've got stellar mass. So this is called the stellar mass to halo mass relationship. In the dots, we've got measurements of halo mass from kinematics, and these are obtained from using the rotation curve for small samples of galaxies, maybe 200 galaxies, and these are assessed on their ability to reproduce abundance matching relationships, which is this gray band here, and so I'll explain abundance matching in a minute, but that's a prediction for the halo mass at a given stellar mass from cosmology. We're doing three things differently to them. We're doing it for a much larger sample of galaxies using a weaker piece of kinematic information. So rather than have the full rotation curve, we just have this integrated H1 line width. They traditionally do it using a stellar mass-based abundance matching. We're using baryonic mass, and we're using a new abundance matching relationship specifically designed for the H1 selected galaxies. i.e. galaxies that appear in alpha that we're studying. And finally, we're comparing the full posteriors on mass and concentration in 2 dimensions, rather than just marginalizing over concentration and comparing on the ability to reproduce the relationship like this. So abundance matching. So abundance matching is an empirical method that connects the dark matter halos we see in dark matter only simulations to large-scale galaxy surveys. It's based on a simple ansatz, which is the heaviest galaxies live in the heaviest halos. So what you do is you rank galaxies by their mass. Usually this is done with stellar mass. We're doing it with baryonic mass because we believe baryonic mass is more fundamentally connected to the halo mass. There's evidence for this in things like the Tully-Fisher relationship, which is tighter if you use baryonic mass rather than stellar mass. So we're ranking galaxies by baryonic mass, and we're ranking halos by their MV, their halo mass. So what you do is you assign galaxies to halo by saying the heaviest galaxy in our simulation is around the heaviest galaxy in our observed survey. The second heaviest galaxy in the survey is in the second heaviest halo in the simulation, and so on. And then you add scatter to this to account for the stochasticity in galaxy formation. So, you know, for example, on average, we expect the second heaviest galaxy to live in the second heaviest halo, but because of this randomness associated with galaxy formation, with cosmic accretion, this relationship could become a bit jumbled. And so we take our baryonic mass function from SDSS cross alpha, and we get our halo catalog from the Uchu halo catalog, which is a halo catalog from dark matter only simulations. Sorry, which is a halo catalog which is publicly available and has a very large box size, which is important for work like this.
How do you do the jumbling, the scattering from?
How do you do the scattering? So it's actually quite. Sorry, may I have some water, please?
Yes.
I'm feeling a bit dizzy.
Thanks, Rachel. Also, if you can give this a break or something.
Yeah, I'm not sure.
Right.
I'll continue here.
All right, take your time. No need to. It wasn't an urgent question.
Yeah.
Maybe we can open the window.
You need like blood sugar or something, we can definitely do that as well.
No, I think I'm good. I think I'm good. Oh god, let's try that.
It can't hurt, right? I'm not going to ask her this because give them a break, but can you not have more than one galaxy per halo?
Something like halos that orbit around bigger halos, and so you get from the on one galaxy, which on one halo can only have one galaxy apart from the lines that are in two halos.
Okay, fine.
So for the abundance matching regime model, a core assumption is that in each halo and in each sub-halo you have one galaxy.
Right. Whereas when we do things like halo occupation distributions, we're assuming we've only resolved down to some halo mass. So actually what we're treating as one big halo is actually.
Yeah, exactly. And then you populate your one big halo, your central halo, with satellites.
Yeah.
And then HOD has its origins in the time before you resolved subhalos. But you can actually use abundance matching to constrain your HOD. So if you assume that abundance matching ansatz that each subhalo has a satellite galaxy as true, then you can constrain your HOD model using abundance matching. but HOD has its own advantages as well. I'll have to talk about that after.
Let us know if you want to stop at any point.
Yeah, no, I think I'm good now. So where were we? Yeah, so you're right. The Ansatz is the heaviest galaxy, lives in the heaviest halo, and the second heaviest in the second heaviest halo. So you can go down all the way associating galaxies with halos. So to show this, how this is done, computationally for the whole catalog. On the left here, we have the baryonic. We have the abundances of galaxies above a certain baryonic mass from SDSS cross alpha alpha. And on the right here, we've got the abundances of halos above a certain mass from the Uchu catalog. And so this will be the number of galaxies above a given mass in a fixed volume, 1 megaparsec cubes. So this ranking procedure I described is equivalent to matching the abundances, which is on the y-axis, between the halo mass and the baryonic mass. So you say for a halo mass of 10 to the 10, there's about 3 times 10 to the minus 2 abundances per megaparsec cubes, which is the same as for 10 to the 11 halo mass. So you assign your 10 to the 10 baryonic mass galaxy into a 10 to the 11 mass halo, and you go all the way down doing that. And then the scatter is then you take the assigned stellar mass, and then you add the assumption is that the scatter is a Gaussian log normal. So you'll add 0.2 decks of scatter via stochastic procedure. Well, yeah, you'll just add a random amount of scatter to each galaxy drawn from the Gaussian, and then you'll repeat that over many realizations. Good. But it's not quite that simple because you need your distribution of galaxy masses with the scatter added to be equal to what is observed on the real world. So you have to do something called deconvolution, where you basically make it self-consistent. Okay, so in particular, we're as I was saying, most abundance matching methods are based on optically selected galaxies. So by that I mean galaxies that appear in optical surveys such as the SDSS. However, if you look at the galaxies in optical surveys, they're much more strongly clustered than the galaxies in H1 selected surveys. So there on the right is the galaxies from alpha alpha, which are much more weakly clustered than optically selected galaxies. So the fact that the galaxies are weakly clustered suggests they live in weakly clustered halos. And if you look in simulations and you look at the weakly clustered halos, they have different properties at fixed halo mass to the strongly clustered halos. This is called halo assembly bias. So what you want to do is you want to construct an abundance matching model that is able to reproduce the properties of the observed galaxies. So in particular, I didn't explain abundance matching. You test that it works, and you constrain the 3 parameters like the amount of scatter using clustering. So you want your model to be able to reproduce the clustering of the galaxy population you're using. So I take the model of statistical Ekatau, who's also at Oxford, and what you find is that if you have 0.4 decks of scatter, which is quite a lot compared to the normal optically selected galaxies, and you put a cut on halo formation time, such that you only include halos from the simulation that form later, then this is able to generate the weak clustering that you observe of your sample. And so this has theoretical motivation in that we think that we think that galaxies that are gas rich, we think they formed later in later forming halos, and so they're still increasing the cosmic supply of gas, hence they're still star forming. Good. And so normally, as I was saying, abundance matching is used to assign a galaxy to a halo. However, we want a posterior on mass and concentration from for each galaxy with the input as the galaxy's baryonic mass. So we formulate a Bayesian formulation of inverse abundance matching, which gives you the probability of the halo mass and the concentration given the baryonic mass, which looks like this. Okay, now to our kinematic model. So basically what we want to construct a Bayesian forward model for the H1 line width. Because the H1 line width is quite a complicated quantity. You're basically integrating over the whole, all the gas in the galaxy to get that spectrum. So the modeling is a bit involved. So to go through the core assumptions, so we're using H1 because basically it can cool and quickly form a dynamically cold disk. So we assume the galaxy is axisymmetric, and it's got a thin H1 disk in it, and at each radius of the disk you have the gas moves in a circular orbit. This means it directly traces the underlying gravitational potential, and hence, the potential sourced by the dark matter. So the 3 parameters in our model are the mass, the concentration, and 7 galaxy parameters. So these describe the distribution of the baryons and other properties of the galaxy. So the galaxy parameters are the H1 mass, the stellar mass, the distance, and the inclination. So we get the priors for these directly from observation. So as I said, alpha measures an H1 mass. To ensure that uncertainties are properly included in our model, we use these observations to inform our priors. So for example, the prior on the H1 mass is a Gaussian with mean given by the observed alpha value, and a scatter given by the uncertainty on the observed value. However, the distribution of baryons, rather than measure these directly, we get these from empirical models. So these are models where you measure the mass of the H1 disk for a whole sample of galaxies. Then you measure the size of the H1 disk using resolved data, and you find there's a very tight relationship. Whereas in alpha, you don't measure the actual size of the H1 disk, so you're reliant on these scaling relationships. And so these models have quite large scatter on them, but we have again, by applying the scatter as uncertainties on the prior, we're able to include that. So we've got our 3 parameters and our priors, and now we need to construct a model H1 line widths compared to observations and the likelihood. So first, we use our 3 parameters to form 2 things. Up top there, we have the rotation curve. So this is the circular velocity of the galaxy as a function of radius. This is made up of the contribution from the baryons and from the dark matter. And so you sum those together in quadrature to get the circular velocity, the total circular velocity of the galaxy, and this will determine, this is the velocity with which the gas moves in circular orbits at each radius on the x-axis. The second component we need is the surface density of the H1 gas, which we have on the bottom here. So again, we use our scaling relationships to get the scale length of the H1 gas. We assume it sits in an exponential disk, and we add a cutoff here, a core in the center. And so what happens is at very high density, the H1 gas turns to molecular clouds. This is inserted a bit. This is, and so this fix might not be exactly right for each galaxy, but we test that our overall model isn't sensitive to how exactly we cut off the H1 density at high values. And finally, to get from the rotation curve up top and the H1 surface density to our H1 line width, we use this equation here. So on the x-axis of the H1 line width, we have the observed velocity. So this is the velocity. This is the flux observed at the wavelength equivalent to some radial velocity relative to the galaxy's systemic velocity. So the H1 flux at the wavelength equivalent to the observed velocity is equal to the integral over all points on the gas disk whose rotation velocity projected along the line of sight is equal to V, weighted by the H1 surface density of the gas at each point on the disk. And then this final factor is here to account for the intrinsic H1 dispersion of the gas. Any questions on that? So because we're using unresolved data to generate our kinematic model, there's quite a lot of assumptions that go into it. But what we do is we verify this using resolved data. And by resolved data, I mean rotation curves, where you measure the rotational velocity of the gas at each radius of the galaxy. So what we do is we generate mock H1 line widths using rotation curves from a survey called Spark and the H1 densities. And essentially what we see is this high resolution data is a good match to our approximations. So we believe the model works. I'll skip this, but essentially inclination is an important factor. If you have questions about that, we can talk about it at the end. So the posteriors from the kinematics are going to look slightly oddly shaped. So I'm going to talk you through an idealized example to try and explain the shape. So on the x-axis here, we've got halo mass, and on the y-axis, we've got concentration. So in the simplest possible model, you just assume that the line width of this idealized galaxy is just equal to twice the maximum velocity of the dark matter halo. And so this is what the Tully-Fisher relationship of 1977 was based on. And so that just gives this blue posterior here, which is just almost linear. And so that's what you get if you take a really naive model where you don't account for the distribution of the gas or anything. However, in the red, the green, and the yellow, this is where you include our model with the full gas disk. And what you find is that at high halo concentration, the model where the line width is just equal to twice the circular velocity of the halo is a good model. But towards low concentration, it veers away from it. And so as the concentration of the dark matter halo decreases, what happens is the dark matter is more and more spread out. So its maximum circular velocity occurs at a larger and larger radius, and eventually it occurs at such a large radius that it no longer occurs within the gas disk. Hence, you get it deviating from the naive expectation. So basically, this justifies why you need to model the whole H1 disk rather than just using a simple model. And so here we fixed the galaxy's inclination before, but now we're just tilting the galaxy through different inclinations. The projection of the rotational velocity of the galaxy along the line of sight, there's a factor of sine inclination. And so what you see as inclination goes from high to low, high 90 degrees being when the galaxy is edge on, and low to when the galaxy is almost face on. So all of the direction of its rotation is almost facing completely away from you. So there's a massive correction. You find it sweeps out a massive posterior, sweeps out to a very high halo mass and concentration. So basically what this means is that if the galaxy has a well-constrained inclination, then you expect quite a tight posterior. Whereas if the galaxy has a poorly constrained inclination, then you can basically, the posterior is expected to spread out over all the different inclinations we see there. Cool. Right. So now we're going to compare the posteriors from abundance matching and kinematics, galaxy by galaxy. So here's a typical galaxy in our sample. Up top there, we have the raw H1 spectrum, and we've got the line width shown in pink. And in the bottom panel, we have our posteriors on halo mass on the x-axis and concentration on the y-axis. In red is the posterior from abundance matching, which is just a well-defined area. In the blue, we have the posterior from the kinematic model. As we can see, it's a band. But it's thicker than before because we've now marginalized over all the uncertainties, like the inclination, the distance, the stellar mass. Actually, one thing I don't think I mentioned is that the reason it is degenerate between mass and concentration is you can generate the same line with either a halo with very high mass, which is very spread out, such that most of the mass sits outside the gas disk, or you can generate the same line with a halo with very low mass, which is very concentrated. So all the mass sits in the center. So there's a perfect degeneracy there. Hence you get the long bands. We see that the red and the blue posteriors are in good agreement. They overlap. So that means we can combine them to get a tight constraint on halo mass and concentration in green. And so this makes up around 2/3 of our sample. In this bottom panel here, rather than fitting the cuspy NFW profile, we're doing the same, but fitting a cooled Burkett profile to our kinematic model. Again, we get qualitatively similar results, but with a slightly different shape due to the different shape of the halo profiles. The second type of galaxy we get in our sample is like this. Here we see the constraints from kinematics are very weak for both Burkett and NFW. And so the reason for this can be various. For example, there's a very high uncertainty on the line width. The inclination of the galaxy is not very well known, or the distance to it isn't well known. If you don't know any of these things, they're degenerate with the mass and the concentration, so you just get a very large posterior. And this occurs for around 1/5 of our sample. The third, more interesting case is where the halo mass, the halo mass and concentration inferred from kinematics in the blue and the purple are in tension with the abundance matching prediction. In particular, the dynamical mass implied by the H1 line width is lower than that expected from abundance matching. We see that this tension is relieved somewhat if you fit a Burkett profile instead of an NFW profile. The posteriors are in better agreement. And so this behavior occurs mainly for galaxies with low baryonic mass. And then the final example you see is we've got a slight disagreement again, but it's the opposite way around. This time, the dynamical mass implied by the kinematics is higher than the expectation from abundance matching. And you can get a higher dynamical mass by either having a higher concentration, so up on the y-axis where you have more of the halo smushed into a smaller area, or or by just increasing the mass on the x-axis. Right. So the next question to ask is why do we see that there's tension for some of these galaxies? So here we're going back to the raw data and we're just plotting the H1 line width against the galaxy mass. And so what you see is it's not very tightly correlated. In the first panel we plotted the whole sample. In the second panel we plot just the intention galaxies for the NFW profile, and in the final plot we show only the intention galaxies for the Burkett profile. So what we see is that the galaxies that are intention mostly have a low line width compared to their baryonic mass, with a small population on the right the other way around. and so we perform quality cuts on our data, like removing galaxies with poorly known line widths and things like this, and we find that the tension persists. So this is it. This view is interesting because for the spark galaxies, which is commonly studied much smaller samples of galaxies, you see a very tight correlation, which is shown in pink. But when we look at this much larger sample of galaxies, the tightness of that correlation is lost. So the simple interpretation of this is that for this larger population of galaxies, we're seeing that there's a lot of variety in how the dark matter is distributed within the center of the galaxy. Yeah, so it seems that this new population of galaxies we're looking at in higher numbers seems to be very different to this smaller previously studied sample of galaxies.
Great. Can you just help me get a physical picture for what it means if galaxies have a, got it right, a low line width relative to their baryonic mass compared to your, your sparks data? What is that saying? They've got less H1 gas in. The H1 gas is distributed differently.
So there's a number of things that it could mean. So if we assume that H1 gas is well behaved between galaxies, and we think it is, H1 gas, it just cools and forms gas disks and tends to be well behaved. So in that case, most of the potential that sources the line width is sourced by the dark matter. So if it's got a low line width, it's got less dark matter in it, essentially. And so if it's got a low line width compared to its baryonic mass, rather than say having basically we have something we call the efficiency of galaxy formation, which is the baryonic mass divided by the halo mass. If all the baryons available to the galaxy, condense and if all the cosmologically available baryons condense and form the galaxy, then this ratio is just equal to the baryon fraction, so 0.2. However, galaxy formation isn't very efficient, so what you tend to find is it can vary from so you can find at most you find a fifth of the cosmologically available baryons have actually formed the galaxy, but this can get as low as 1 in 1,000. So what this is saying is that, and so the trend predicted by abundance matching is that this galaxy formation efficiency correlates tightly with baryonic mass. So at a baryonic mass of 10 to the 10, you expect about 20% of the available baryons to form the galaxy. However, as you drop to a baryonic mass of 10 to the 8, you expect that to fall to 1 in 1,000. However, what this wide variety is showing is, because we think that the line width is tightly correlated with the halo mass, this seems to suggest that at fixed baryonic mass, there's a wide variety of halo masses, and so a wide variety of galaxy formation efficiencies, which is in disagreement with abundance matching.
Okay. All right.
So abundance matching at fixed baryonic mass predicts a small distribution of halo masses, whereas what this diagram implies is actually it's more varied.
Got it. Thank you.
And so the next thing we can do is we've got these posteriors for each individual galaxy, but then we can stack them all on top of each other and see what the relationship looks like for the whole group. So what we do is we take the posteriors and we stack them in narrow bins of baryonic mass. So we're putting all the galaxies with a similar baryonic mass, and then we're taking the posteriors and combining them together. So this is what that looks like. So in red, we've got the abundance matching relationship. In blue, we have the kinematic relationship. On the right there, the histogram is the number of galaxies in each bin, which is a lot. The dashed line aligns a constant baryonic mass over halo mass, so constant galaxy formation efficiency. Just standing again. So here we have the omega b over omega m. So that's the cosmologically available baryon fraction. So once you get close to that line, galaxy formation is reaching close to maximum efficiency, where all the cosmologically available baryons form the galaxy. So what we see here is, firstly, there's a lot of scatter in the blue relationship. So in part, this is from the galaxies we saw in 2 slides before, where some of them just have very weak constraints from kinematics due to things like poorly known line width. However, we also, in part of it, is due to that large scatter we just discussed, where there seems to be a lot of different halo masses at a fixed baryonic mass. We see that the red and the blue are in good agreement. However, at low baryonic mass, we see that the blue deviates, the solid blue line, which is the mode of the kinematic distribution, deviates from the mode of the abundance matching distribution, which is the solid red line. And so this is another manifestation of that population of galaxies, which isn't the whole sample at a given baryonic mass, but a sizable fraction, which are in disagreement. And finally, we see that the kinematic relationship is approximately a power law linear. So this is more obvious if you remove some of the galaxies with the worst scatter, the relationship sort of tightens and narrows. Whereas on the other hand, for abundance matching, the posterior, it starts off narrowed down here and then it spreads out and it is nonlinear essentially. And so for comparison, in the green dashed line, that's what you get from the classic optical relationship, whereas the red is what you get if you use the abundance matching relationship appropriate for this population of galaxies. So basically the difference is the H1 selected abundance matching model predicts much more galaxies with high galaxy formation efficiency, so closer to omega b over omega m. So comparisons of other studies. So what we find is that for most galaxies, our kinematic halo properties and our abundance matching halo properties are in good agreement. This is in agreement with other studies on smaller samples like SPARC, which find that abundance matching gives around the right mass for the dynamics, which is reassuring. Because abundance matching, this is based on dark matter only simulations. It's based on the cosmological clustering of dark matter, whereas kinematics is looking at a galaxy, looking at the motion and inferring a missing mass. So these two things didn't necessarily have to agree. So it's definitely not trivial that they do. We see that once we switch to our H1 selected model, there's no tension at the high mass end, whereas if we'd used our old optically selected abundance matching model, there would have been tension at the high mass ends. This is relevant to studies in literature, which finds that late type galaxies and early type galaxies live in different mass halos at a fixed stellar mass. So in particular, in grey, here's the classic optically selected abundance matching. In blue, these are late type galaxies, and this is from a solid positive R. And what they find is that these late type galaxies are in disagreement with the abundance matching predictions. If they switch to our H1 selected model, then this disagreement would vanish. The caveat to that, I would say, is that our H1 selected model is capable of reproducing the correct clustering for the galaxies in the population, which is good. However, the theoretical picture for why some galaxies are rich in gas and why some galaxies are poor in gas, and so we expect H1 selected galaxies to be rich in gas, is actually seems quite complex. And if you remember, our model just had a cut on halo formation time. Whereas if you look in simulations and you look for a correlation between the amount of gas in the galaxy and the halo formation time, you don't find it particularly strongly. So maybe although this model can reproduce the correct clustering, it's not got a solid theoretical motivation yet, and maybe it needs to be expanded to include other factors such as the environment, the anisotropy, and things like this. So the model can relieve tension, but it's not sort of complete. And finally, there's been a lot of recent interest in dark matter-free galaxies, such as AGC 114905. So this is in agreement with the population of these galaxies we found, which have very low line widths, and so their kinematic mass under predicts their abundance matching, which suggests that these galaxies have a very low amount of dark matter, at least within the H1 gas disk. So in agreement with these studies, which find dark matter-free galaxies. However, these studies tend to be very controversial. There's always a lot of debate about systematics and kinematic studies, such as inclination. I had a couple of whole slides on inclination that I skipped over, but basically, there's always the argument that you're not correctly accounting the inclination. For example, we calculate the inclination using the SDSS image, but we don't necessarily know that the H1 gas disk is aligned with the optical disk. This model seems to work well for the spark galaxies, but as I was explaining before, we're now looking at a new population of galaxies. So I think it remains to be seen whether these same approximations we use for spark hold up to this new population. And finally, there's a question of can you even have stable galaxies, stable stellar disks forming in galaxies without dark matter? Some people argue this implies new dark matter physics. So I think it will be interesting to see as we get new surveys such as the SKA, and we observe more galaxies like this, whether this dark matter deficiency holds up or not. And finally, maybe more interesting from the cosmology perspective, getting back to the aim of the talk, which was combining constraints from different probes to improve our constraints on halo properties. So we combine the kinematics in blue and the abundance matching in red to get the tighter green constraint. And what we want to do is we want to quantify how much of an improvement that is for the entire population of galaxies. So we come up with this simple I metric. So 6 sigma AM is the size of the halo mass constraint from abundance matching. So we've marginalized over concentration now. Sigma AM plus kinematics is the size of the combined constraint on the halo mass from combining them together. So basically, an I of 0 means no improvement, whereas an I of 1 means that by combining, your constraint has shrunk to half the size. And what we find is for the whole population of galaxies, combine the constraints for NFW gives a 40% mean reduction in the uncertainty on halo mass. And so this is useful for things such as mapping out the dark matter distribution, mapping out the gravitational potential of the local universe, this sort of thing. The improvement's much less for Burkett, and you can understand this just because Burkett's got a chord profile. It's got a smaller fraction of its dark matter mass right in the center, which is what the H1 disk probes. So there's just going to be more uncertainty there. So future work. So what I did was I constructed a model for the full H1 spectrum. and then I compressed this, the line width summary statistic. So I took the full spectrum and I just compressed it to just the width of it. However, you can just fit to the full spectrum, which is what I do here, and it's quite a good fit, and that gives you much tighter constraints on halo mass and concentration. So that gives you the blue posterior there rather than the grey posterior. And so I've applied this to the whole sample, but the problem I'm dealing with at the moment is the H1 spectra of these galaxies. This is a well-resolved, neat, symmetrical example. You get lots of asymmetries. The H1 disk can have holes in, so you sort of get bits missing from the center. And also some galaxies just have low signal to noise. So you need a way to model all of this and sort of properly take into account the uncertainties. So that's what I'm doing now. Future work, as I was saying, the H1 distribution, our model where we just took an exponential disk and then just took a core in the center to account for the conversion of H1 to molecular gas. That's a simple model. If we want to fit the full spectrum, we need a better model. And we also want a model that we can apply to different types of galaxies, like early type galaxies. The second thing we can do is we can combine our H1 gas data, which, as I said at the start, that probes fairly far out into the halo. We can combine that with data from the center from the optical. And so by combining these together, we sort of sample the dark matter distribution at the very center of the halo, at the very center of the galaxy, and further out into the halo. This provides essentially 2 data points instead of 1 and will give us tighter constraints. The other thing I'm interested in is combining this kinematic and abundance matching measures with other probes. In particular, weak lensing is particularly interesting because weak lensing traces the dark matter distribution at larger radii from the galaxies. The problem is you just get very weak constraints from the shear of a single galaxy. So you typically do this in stacks. So what you'll need is some sort of hierarchical model where your whole population of galaxy is able to produce the stacked weak lensing data, as well as producing the line width of each individual galaxy. And finally, with future surveys such as MITE in the SKA, you can apply this method to many more galaxies. I'll leave my conclusions up here and take questions.